and anaerobic respiration, two systems that can supply ATP relatively quickly and without requiring oxygen, Table 9.3. The ability of aerobic respiration to supply ATP at the onset of exercise lags behind that of creatine phosphate systems and anaerobic respiration. This explains the lag between the onset of exercise and the need for increased oxygen. The elevated oxygen consumption that occurs after exercise has ended is called oxygen recovery consumption. A portion of recovery oxygen is used to repay the oxygen deficit incurred at the onset of exercise, but most of the recovery oxygen is used to support metabolic processes that restore homeostasis after it has been disturbed during exercise. Such disturbances include exercise-related increase in body temperature, changes in intra- and extracellular ion concentrations, and changes in metabolite and hormone levels. Recovery oxygen consumption generally lasts minutes to hours depending on the individual physical conditioning and on the length of the intensity of the exercise session. In extreme cases, such as following a marathon, recovery oxygen consumption can last as long as 15 hours. Slow twitch and fast twitch fibers. There are two major types of skeletal muscle fibers, slow twitch and fast twitch. Not all skeletal muscles have identical functioning capabilities. They differ in several respects, including the composition of their muscle fibers, which may contain slightly different forms of myosin. The myosin of slow twitch muscle fibers causes the fibers to contract more slowly and to be more resistant to fatigue, whereas the myosin of fast twitch muscle fibers causes the fibers to contract quickly and to fatigue quickly. Table 9.4. The proportion of muscle fiber types differs within individual muscles. Slow twitch oxidative muscle fibers. Slow twitch oxidative muscle fibers, SO, type 1 fibers, contract more slowly and have better developed blood supply, have more mitochondria, and are more fatigue resistant than fast twitch muscle fibers. In women, type 1 alone or in conjunction with type 2A are the largest diameter fibers. Slow twitch muscle fibers respond relatively slowly to nervous stimulation. The enzyme on the myosin heads responsible for the breakdown of ATP are called myosin ATPase. Slow twitch fibers break down ATP slowly because their myosin heads have a slow form of myosin ATPase. The relatively slow breakdown of ATP means that cross-bridge movement occurs slowly, which causes the muscle to contract slowly. Aerobic respiration is primarily sourced for ATP synthesis in slow twitch muscle fibers, and their capacity to perform aerobic respiration is enhanced by plentiful blood supply and the presence of numerous mitochondria. They are called oxidative muscle fibers because of their enhanced capacity to carry out aerobic respiration. Slow twitch fibers also contain large amounts of myoglobin, a dark pigment similar to hemoglobin in red blood cells, which binds oxygen and acts as an oxygen reservoir in the muscle fibers, and when the blood does not supply an adequate amount. Myoglobin thus enhances the capacity of the muscle fibers to perform aerobic respiration. Fast twitch muscle fibers. Fast twitch muscle fibers, type 2 fibers, respond rapidly to nervous stimulation, and their myosin heads have a fast form of myosin ATPase, which allows them to break down ATP more rapidly than slow twitch muscle fibers. This allows their cross bridges to release and form more rapidly than those in slow twitch muscle fibers. Muscles containing a high percentage of fast twitch fibers have a less well-developed blood supply than muscles containing a high percentage of slow twitch fibers. In addition, fast twitch muscle fibers have very little myoglobin and fewer and smaller mitochondria. Fast twitch muscle fibers have large deposits of glycogen and are well adapted to perform anaerobic respiration. However, the anaerobic respiration of fast twitch muscle fibers is not adapted for supplying a large amount of ATP for a prolonged period. The muscle fibers tend to contract rapidly for a shorter time and to fatigue relatively quickly. Fast twitch muscle fibers come in two forms, type 2A or fast-twitch oxidative glycolytic FOG fibers, and type 2B, or fast-twitch glycolytic FG fibers, table 9.4. The type 2A fibers rely on both anaerobic and aerobic ATP production, whereas type 2B fibers rely almost exclusively on anaerobic glycolysis for ATP production. In men, type 2A are the largest diameter fibers. Distribution of fast-twitch and slow-twitch muscle fibers. The muscles of many animals are composed primarily of either fast or slow-twitch muscle fibers. A chicken or pheasant breast, which is composed mainly of fast-twitch fibers, appears whitish because it is relatively poor blood supply and lack of myoglobin. The muscles are adapted to contract rapidly for a short time, but they fatigue quickly. By contrast, the meat of a chicken leg or a dark breast is composed of slow-twitch fibers and appear reddish or darker because of their relatively well-developed blood supply and larger amounts of myoglobin. These muscles are adapted to contract slowly for a longer time and to fatigue slowly. The distribution of slow-twitch and fast-twitch muscle fibers is consistent with the behavior of these animals. For example, pheasants fly relatively fast for short distances, whereas ducks fly more slowly for long distances. Human muscles exhibit no clear separation of slow-twitch and fast-twitch muscle fibers. Most muscles have both types of fibers, although the number of each varies for each muscle. The large postural muscles contain more slow-twitch fibers, whereas the muscles of the upper limbs contain more fast-twitch fibers. The distribution of slow-twitch and fast-twitch muscle fibers in a given muscle is fairly constant for each individual and appears to be established during early development. Sprinters have a greater percentage of fast-twitch fibers, whereas long-distance runners have a higher percentage of slow-twitch muscle fibers in their lower limb muscles. Athletes who perform a variety of anaerobic and aerobic exercises tend to have more balanced mixture of fast-twitch and slow-twitch muscle fibers. Effects of exercise. Neither fast-twitch nor slow-twitch muscle fibers can be easily converted to muscle fibers of the other type without specialized training. Training can increase the size and capacity of both types of muscle fibers so that they perform more efficiently. Intense exercise that requires anaerobic respiration, such as weightlifting, increases muscular strength and mass and causes fast-twitch muscle fibers to enlarge more than slow-twitch muscle fibers. Conversely, aerobic exercise increases the vascularity of muscles and causes slow-twitch muscle fibers to enlarge more. Aerobic exercise training can convert some fast-twitch muscle fibers that fatigue readily, type 2B, to fast-twitch muscle fibers that resist fatigue, type 2A. In addition to changes in myosin, increases occur in both the number of mitochondria and in muscle fibers and in their blood supply. Weight training following by periods of rest can convert some muscle fibers from type 2A to type 2B. However, a type 1 muscle fiber cannot be converted to a type 2 fiber, and vice versa. Through specific training, a person with more fast-twitch muscle fibers can run long distances, and a person with more slow-twitch muscle fibers can increase the speed at which he or she runs. In response to exercise, a muscle increases in size or hypertrophies and increases in strength and endurance. Conversely, a muscle that is not used decreases in size or atrophies. For example, muscular atrophy occurs in an arm or leg that is placed in a cast for several weeks. Because muscle fibers numbers do not change appreciably during most of a person's life, atrophy and hypertrophy result from changes in the size of an individual's muscle fibers. As a fiber increases in size, the number of myofibrils and sarcomeres increases. The number of nuclei in each muscle fiber increases in response to exercise, but the nuclei of muscle fibers cannot divide. New nuclei are added to muscle fibers because small satellite cells near skeletal muscle fibers increase in number in response to exercise and then fuse with the skeletal muscle fibers. Other elements such as blood vessels, connective tissue, and mitochondria also increase in number. Atrophy due to lack of exercise results from a decrease in all these elements without a decrease in muscle fiber number. However, severe atrophy, as occurs in elderly people who cannot readily move their limbs, does involve an irreversible decrease in numbers of muscle fibers and can lead to paralysis. The increased strength of trained muscle is greater than would be expected if the strength were based only on the change of muscle size. In a trained person, part of the increase in strength results from the nervous system's ability to recruit a large number of motor units simultaneously to perform movements with better neuromuscular coordination. In addition, trained muscles are usually less restrictive by exercise adipose tissue. Metabolic enzymes increased in hypertrophied muscle fibers, resulting in a greater capacity to take in nutrients and produce ATP. Improved endurance in trained muscles as a result is in part due to improved metabolism, increased circulation due to the exercise of muscle, increased numbers of capillaries, and more efficient respiration, and a greater capacity of the heart to pump blood. The rate of metabolism in skeletal muscle differs before, during, and after exercise. As chemical reactions occur within cells, some energy is released in the form of heat. Normal body temperature results primarily from this heat. Because the rate of the chemical reactions increases in muscle fibers during contraction, the rate of heat production also increases, causing the rise in body temperature. After exercise, increased metabolism resulting from recovery oxygen consumption helps keep the body temperature elevated. But sweating and vasodilation of blood vessels in the skin speed heat loss and body temperature within the normal range. See chapter 25. When body temperature declines below a certain level, the nervous system responds by inducing shivering, rapid skeletal muscle contractions that produce shaking rather than coordinated movements. During shivering, the muscle movement increases heat production up to 18 times that of resting levels. And the heat produced can exceed the amount produced during moderate exercise. Thus, shivering helps raise body temperature to its normal range.